Bismillahirrahmanirrahim. Assalamu alaikum. Welcome back to Physics Mathematics Hub, the channel where complex physics and mathematics problems meet easy explanations and smart solutions. In today's video, we are solving exercise 1.34 from the book of Quantum Mechanics by Nouredine Zettili. Now let's head straight to the problem statement. A simple one-dimensional harmonic oscillator is a particle acted upon by a linear restoring force f of x equal to minus m omega square x. Classically, the minimum energy of the oscillator is zero because we can place it precisely at x is equal to 0, its equilibrium position, while giving it zero initial velocity. Quantum mechanically, the uncertainty principle does not allow us to localize the particle precisely and simultaneously have it at rest. Using the uncertainty principle, estimate the minimum energy of the quantum mechanical oscillator. We are given the following data in the exercise. Linear restoring force f of x is equal to minus m omega square x. Classically, a harmonic oscillator can have zero energy because we can place the particle exactly at its equilibrium position x is equal to 0 and give it zero velocity. So there will be no kinetic energy and no potential energy at equilibrium position. But in quantum mechanics, things work differently. According to Heisenberg uncertainty principle, we cannot know both the position and momentum of a particle with absolute certainty. That means we cannot place the particle precisely at x is equal to 0, simultaneously say its momentum is 0. Hence the particle must have some energy even at rest. We have to use the uncertainty principle to estimate the minimum energy of the quantum mechanical harmonic oscillator. The minimum energy is denoted by E naught. As we have discussed the given and required data, it's time to move towards the solution. To estimate the minimum energy, the ground state energy of quantum harmonic oscillator using Heisenberg uncertainty principles, we use the total energy equation of quantum oscillator, which is the sum of the kinetic and potential energies. Here E is the total energy of the system, which is equal to kinetic energy plus potential energy of the system. Putting values of kinetic energy and potential energy, we get E is equal to P square divided by 2m plus 1 over 2 kx square. E is equal to P square divided by 2m plus 1 over 2m omega square x square. Here we put the value of kx, which is equal to m omega square x. To use the uncertainty principle, we can write the above equation as E is equal to del P square divided by 2m plus 1 over 2 m omega square del x square. Say this is equation 1, where del x is the position uncertainty and del P is the momentum uncertainty. For the particle in a minimum uncertainty state, the Heisenberg uncertainty equation is given by del x into del P is equal to h cut divided by 2. Solving for del P. Del P is equal to h cut divided by 2 del x. Say this is equation 2. Putting equation 2 in 1, we have E is equal to h cut divided by 2 del x whole square divided by 2m plus 1 over 2 m omega square del x square. Simplifying the above equation, we get E is equal to h cut square divided by 8m del x square plus 1 over 2 m omega square del x square. Let this is equation 3. Here, here energy is the function of del x. Therefore, to minimize the energy, we take derivative of the above function E with respect to del x. So, dE divided by d del x is equal to d divided by d del x into the given function. At minimum energy, the rate of change of energy with respect to position is 0. So we can write dE divided by d del x is equal to 0. Now, finding the derivative of the function E with respect to del x, we get dE divided by d del x is equal to minus 2 h cut square divided by 8m del x cube plus 1 over 2 m omega square 2 del x, and this is equal to 0. After simplification, we get minus h cut square divided by 4m del x cube plus m omega square del x equal to 0. Further simplification gives h cut square divided by 4m del x cube is equal to m omega square del x. Multiplying del x cube on both sides, we get h cut square divided by 4m is equal to m omega square del x power 4. Now solve the above equation for del x. We get m omega square del x power 4 is equal to h cut square divided by 2m. We can write this as del x4 is equal to h cut square divided by 4m square omega square. Taking square root on both sides, we get del x square is equal to h cut 2m omega. Substitute the expression for uncertainty in position back into the energy equation 3. So equation 3 implies that the minimum energy is equal to h cut square divided by 8m into h cut divided by 2m omega, which is the value of del x square plus 1 over 2m omega square into h cut divided by 2m omega. The minimum energy E naught is equal to h cut omega divided by 4 plus h cut omega divided by 4. We get the minimum energy is equal to h cut omega divided by 2. Therefore, the total minimum energy of the quantum mechanical harmonic oscillator is h cut omega divided by 2. So that was the complete step-by-step solution to our problem. Now let's quickly go over the key points and wrap it up with the conclusion. In conclusion, we find that classically a harmonic oscillator can have zero minimum energy by setting the particle exactly at the equilibrium point with zero velocity. Quantum mechanically, due to Heisenberg uncertainty principle, we cannot simultaneously know the particle's exact position and momentum. As a result, the particle must have some non-zero energy, even in its lowest energy state called zero-point energy. This result shows that even at absolute zero temperature, a quantum harmonic oscillator still possesses this non-zero energy due to quantum fluctuations. This phenomena has real physical implications in many fields like vibrations of atoms in solids, phonons. Atoms in a solid can never be completely at rest even at absolute zero temperature. Zero-point energy keeps them slightly vibrating always. Quantum field theory, or we can say vacuum energy. In quantum field theory, even the vacuum is not really empty. Due to quantum fluctuations, fields like the electromagnetic field constantly fluctuate, creating and destroying virtual particles for tiny moments. And that wraps up our detailed solution to problem 1.34. Thanks for watching Physics Mathematics Hub. If you enjoyed this video, don't forget to like, share, and subscribe to Physics Mathematics Hub for more step-by-step solutions to problems in quantum mechanics. Thanks for watching. Keep learning, stay curious, and as always, Allah Hafiz.